So as I mentioned in previous class, when we say solar cooling and dehumidification, it has three main application. One of the application is for refrigeration to produce low temperature, and then uh, the solar energy, the solar cooling can also be utilized for producing the air conditioning process, where we have to maintain the low temperature as well as we have to control the humidity as well. And then we have the industrial as well as the domestic application for the desiccant dehumidifier. Now, in various part of the world, the humidity is too high to produce the air conditioning process. First, we need to dry that air. Along with that, we have so many application in the industry as well. So we'll discuss in today's class. As in previous class, we discussed the solar refrigeration. As I mentioned, we have mainly two cycle that are utilized for solar refrigeration. One of them you are very familiar with that, which is vapor compression cycle, and the second one is vapor absorption cycle. Now, commercially, there are so many vapor absorption system that are installed at commercial level that are integrated with the solar energy. So mainly when we say the solar refrigerator or the solar air conditioner or the solar chiller, they are by default they mean the vapor absorption cycle. So we'll more focus on the vapor absorption cycle. But now research is going on. How can we run the compressor with the help of solar energy? By using the concept of solar voltaic. I mean, you can convert the solar energy into electricity. I hope we'll discuss in the coming classes how can the photovoltaic. That's one of our topic. I hope if the time permit us, we'll also discuss the photovoltaic. And we also discuss that the input required to compressor, which is W, we can calculate this W work input required to the compressor with the help of the fundamental law, the conservation energy principle. We apply the conservation principle using the steady state energy and mass balance for each of the component, and then we can also calculate the work input required for the compressor. That is the cycle. Normally, this is called the ideal vapor compression cycle. We called it ideal because the processes, for example, 1 to 2 is isentropic compression, but actually it's not an isentropic process. No process can be isentropic, but we can approach to isentropic process. Similarly, the process in the condenser is constant pressure process. Similarly, the process in the evaporator is a constant pressure process, but actually uh, when the when the refrigerant flow inside the tube, those tubes are so small that the pressure doesn't remain constant. Instead, there is always a pressure drop because of the friction of friction flow. And similarly, when the refrigerant expand in the expansion well, it's not always isenthalpic process. We assume that this is an isenthalpic process, right? But actually it slightly varies, slightly deviate from the isenthalpic process. That's why we called it as an ideal isentropic, ideal vapor compression cycle. But the overall performance vary very slightly from the ideal behavior. Uh, So by using the energy balance, we calculated how much input is required to run the compressor by the energy balance. And if we know all of the other component, how much, through the energy balance, we can also evaluate the performance of this solar vapor refrigeration system. Now, the second type of the cycle that we need to focus is vapor absorption cycle. As I mentioned, that basically even the previous one, vapor compression cycle, in that case the main input was electricity. But in vapor absorption cycle, this is basically the heat driven process. There is only a small pump whose input is negligible compared to the input of the remaining system. For example, compared to the input of the generator input, in the form of heat energy, in the form of Q or the heat is so high that we normally neglect the input of the pump. Right? So that's why vapor absorption cycle is mainly the heat driven cycle in which we provide heat input. So this heat input is usually provided in the form of hot water or the saturated steam, and that hot water or saturated steam is normally produced in the solar collector. So that means in order to understand, in order to run this process, vapor absorption cycle, or to evaluate its performance, or even for the design calculation, we first must know what is the requirement for the input. How much QG is required. QG mean input to the generator. How much QG is required, and we know that this QG is we have to, when we say solar energy system. So this QG we have to obtain from this solar collector. You know that if we have a solar collector, let's say this is a flat plate solar collector, so the cold water comes in, so as a result of the heat absorption we have the hot water out, so which is called QU, right? Useful energy. So that useful energy is basically given in the form of the QG, the input to the generator. So in a similar fashion, we have how we have to evaluate the system, because the generator is integrated with all of the four component. The absorber, evaporator, and condenser. So that's why we have to analyze each of the component, and then we can have the input requirement. And once you calculated the input requirement and output requirement, output in that case is basically the heat absorbed. In that case, our objective is to produce cooling, and that cooling can be produced in the evaporator. In evaporator, the heat, let's say QE mean heat absorbed in the evaporator, right? The refrigerant comes in as a liquid, so it absorbs the heat here, so it become vapor. So that means that's a phase change process. So the temperature inside the evaporator remains constant, temperature and pressure. As I mentioned in previous case, basically this is a phase change process, though, so the temperature and pressure remains constant. That's called the latent heat. The heat is absorbed in the form of latent heat, right? So similarly, in the condenser, the temperature remains constant, temperature and pressure remains constant. Similarly, the heat is rejected in the form of the latent heat. Whereas in case of absorber, in absorber, the objective is these refrigerant vapor, because this refrigerant become in vapor form. When it absorbs heat in the evaporator, incoming is liquid, but outgoing is a vapor one. So this refrigerant vapor we need to recirculate again. So there is a process for recirculation. These refrigerant vapor, they are absorbed in an absorbent, right? So once they are absorbed in the absorbent, we then through a pump move into the generator. So in generator we provide heat that again separates the refrigerant vapor and absorbent, but you cannot 100% separate. Let's say if actually in that system they have two different name depending upon the concentration of the refrigerant. For example, the concentration of the refrigerant in the absorber is high, so we called it as strong solution, right? SS, strong solution, because this solution contains the large amount of the refrigerant. But when it is supplied in the generator, then as a result of the heat supplied, that refrigerant vaporize, but it is not 100% vaporized. Some fraction of the refrigerant remains there, so it comes back into the absorber. We called it as weak solution because it contains less concentration of the refrigerant. So this is a weak solution now, which is coming back into the absorber. So again, if you look at the pressure or the operating pressure, absorber, basically there are, when you see the physically a vapor absorption system, you will see just two drum there that are enclosed uh, in some arrangement. We called it as absorption chiller. So in the lower drum they have the absorber and evaporator, whereas in the top drum they have generator and the condenser. So that means The evaporator and absorber, they are at same pressure, I mean at low pressure, and similarly the generator and condenser, they are at high pressure, right? So they are called the high pressure operating component, and absorber and evaporator, they called low pressure operating component. So as I said, basically what we need to do, we have to calculate the value of this QG. I mean, how much QG we have to provide as an input, and this QG is obtained from this solar system, which is also called QU, useful energy. That useful energy obtained from the solar collector is mainly equal to the QG, I mean the energy supplied to the generator. So that we have to calculate that, and similarly, if we supply this much of the energy, and how much output is produced in the evaporator, which is called the heat absorbed in the evaporator, right? So if we know the input and the output, we can calculate the value of the COP, coefficient of the performance, which is equal to the output, which is QE, and the input. Sometimes we also include work input to the pump, right? WP, we also sometimes we include that, because but most of the time we ignore that, because that input is so small that we can neglect that. Additionally, I mean, in absorber, heat is rejected because we try to operate the absorption process at low temperature as possible, because that absorption of the refrigerant is efficient when the temperature inside the absorber is low, because when the refrigerant vapors come into the absorber, that absorption process is an exothermic process. So that means when the liquid refrigerant, they are absorbed in the absorbent, then the heat is released. So if the heat is released, then the temperature inside the absorber will be high. So we need to remove that heat in order to make the absorption process efficient. So we should have some certain arrangement, whether air or water coolant, so that the heat released during the exothermic process should be removed and the absorption process become efficient, right? So this is one of the heat rejection in the absorber, and similarly the heat rejection in the condenser, right? And Q input to the generator. So we can have the overall energy balance as well, and energy and mass balance for each of the component as well, right? In order to calculate the performance of this vapor absorption system. Okay, so as I mentioned, in vapor absorption system, we have two main combination. One of the combination, we called it as the ammonia water system. Another one we call the water and lithium bromide system. Mainly in absorption chiller, we use this combination, water lithium bromide combination. I also mentioned that mainly the water and lithium bromide, they are utilized for the air conditioning process. When you need to produce a chilled water is normally 8 to 15 degrees C when we say the chilled water. So this chilled water is used for the air conditioning process, as we are doing in the FME or in GIK. In GIK, we are producing cooling through the chilled water. Chilled water from the central HVAC plant is a supply to FME, where we have the air handling unit. There is a room we call the air handling unit. So there is a cooling coil. So the chilled water from the main unit, they come in the FME cooling coil. So through the heat exchange of the air, so that cooled air is supplied through the duct in each of the offices. So same procedure applies for the heating process, that they send the hot water from the main unit to FME in air handling unit, where through a heat exchange of the heating coil, the hot air is supplied in various offices. So, but we are talking about in this application, the cooling process. So that means the chilled water is produced by using the water and lithium bromide combination, whereas the ammonia and water combination is applied where you need to produce temperature below 0 degrees C. Right? This is for the producing the temperature above 0 degrees C. I mean, this is mainly for the air conditioning process, but for ammonia and water system, because ammonia has a boiling point very low. I mean about minus 31 degrees C. So that means in normal state you have the temperature of minus 31 degrees C. So that means it can produce much low temperature compared to the water lithium bromide system. Right. We also discuss the advantages of the lithium bromide and disadvantage, right? And also for ammonia water uh, absorption refrigeration system. Now the, I mean, coming back to the calculation, actually, in order to design that system or in order to evaluate the performance of the system, what we need, I mean, we have to integrate with the solar energy utilization. So in that case, if we know that how much QU is required to us, and that QU will be mainly supplied to the generator. So we can have such evaluation through the I mean the energy analysis, right? So we have to perform the energy analysis. As I mentioned previously, we can have the energy evaluation by considering the system as a whole, or we can, I mean, by using the first law of thermodynamics and by using the control volume for each of the component, right? And then each component we consider in a steady state condition. I mean, most of the processes that are in operation, I mean, continuous processes, we assume that they are at steady state flow processes, right? And in that case, I mean, compared to vapor compression process, the mass flow rate is not constant throughout the cycle. If you, I mean, just to show you, like, for example, in that, I mean, compared to vapor compression system, in vapor compression, we have just one refrigerant, right? So that means if we have one refrigerant, the same refrigerant mass flow rate will remain constant throughout the cycle. But this one is a combination of the refrigerant and the absorbent. So that means the mass flow rate will not be constant in that case. For example, in absorber, we have the refrigerant plus absorbent, right? And when through the pump it moves right into the generator, so in generator it separates refrigerant and the weak solution. So again here we have the refrigerant and the absorbent. Similarly here we have the refrigerant and the absorbent, but from the generator we have only refrigerant, right? So that means the refrigerant flow in the condenser and again in the evaporator. So we can say in the condenser and in the evaporator we have just refrigerant only, right? We have just refrigerant only, whereas in the absorber, in absorber and in the generator we have both the refrigerant as well as the absorbent, right? The solution which is leaving the absorber, it is called the I mean concentrated solution, right? Rich solution, whereas the solution which is coming back into the absorber, it has a less concentration of the refrigerant, so it's called a lean solution, right? Okay, and here we have just the refrigerant only. So that's why we need to have the mass balance as well, because mass is not constant throughout. Whereas in case of vapor compression cycle, we can have the properties like the enthalpy as kilojoule per kg, because the mass remains constant. So we can use even the specific enthalpy as well. But here, I mean, the mass, for example, from condenser to evaporator is constant. I mean, up till here is constant, but then from absorber to the generator, the mass is not constant, right? So we have to apply both the energy as well as mass balance to analyze the vapor absorption system. So let's do the vapor absorption system. So the mass flow rate of the refrigerant is not constant throughout the cycle, because we have two fluids. One is as a absorbent, another one is as a refrigerant, right? Okay, so let's do the energy balance. So we have to adopt the same procedure as we did in the vapor compression cycle, that we have to take each of the component and we have to apply the mass and energy balance. Let's say we can start from the first process. Where is the okay? This is one. I mean, the first one is the absorber. So we can start from the absorber. Let's say first we apply the energy balance. So I mean, as a whole, this absorber, what is coming in, what is coming out, that should be equal. So the energy in, right, energy in should be equal to energy out, right? So what is the energy in that case? For example, in case of absorber, so this is in, right? This is in, right? This is also in, and this is also in. And what about the heat? In case of absorber, heat is out, right? Q out in the absorber, right? And then this is going out, right? Yeah. So that means the two component they are coming in and the two component they are going out. And this one is equal to M6H6 plus this is the 12. So M12 H12. So that should be equal to M1 H1 plus QA. So that's the energy balance for the absorber. As you can see, we have the in. This is first one is in, and similarly this 12 is also in to the absorber. This is in. So what is going out? One of the is the energy QA is going out, and similarly from point 1 the energy M1 and H1 is going out. So from here, as you can see, if we know the mass flow rate and the enthalpies, we can calculate that how much heat is rejected from the absorber. So in order to calculate QA, I mean this term will goes on the other side. So QA will be equal to this one minus M1 H1. But before that, you must know the mass flow rate and enthalpy. Whereas you can calculate the enthalpy if you know any of the two property. I mean, if you know, let's say, whether the pressure and temperature, then you can read the properties. I mean, we have the property chart for the refrigerant vapor combination as well as the as well as the properties for the separate refrigerant as well. So similarly, we can apply the mass balance as well because mass is not constant in the absorber. So which mass is coming, which mass is going. Now we will not talk about the heat now. So we can remove the heat, I mean QA, because now we have to see where is the mass, only the mass. So for mass, we have just three stream. One of the stream is from 12, another one is 6, and the next one is 1. So mass balance means the two masses are coming in and the one mass is coming out, right? So that's called the mass balance. So what is coming in? I mean, as I mentioned, this coming in is basically the weak solution. So let's say the mass fraction of the weak solution, mass fraction is represented with, let's say, X, right? So let's say this is for the weak solution. So I mean mass of the weak solution into concentration of the weak solution. So that will become the mass flow rate. Similarly here we have the refrigerant because this is from the evaporator, the refrigerant is coming. Right? So refrigerant is coming. So mass of the refrigerant, MR mean mass flow rate of the refrigerant. This is the mass of the weak solution. So what is going out? The going out is concentrated solution, mass flow rate of the concentrated solution, which is equal to MSS mean the solution, I mean the concentrated solution. Similarly, XSS mean the concentrated solution. So that's the mass balance for the absorber. And similarly, we can have the energy and mass remains constant. I mean, whatever is mass entering in the pump, the same is leaving. So no need for the mass balance for the pump, but we can have the energy balance. So what input we are giving? We are giving work input to run the pump. Right. So what will the energy balance for that? This one, I mean 1 plus WP is equal to the energy H2. So that will be M1 H1 plus the WP, that's equal to M2 H2, right? Similarly, we have this heat exchanger. Basically, these two heat exchanger, they are used to increase the efficiency. I mean, this is preheating. This heat exchanger is for preheating because this solution is sent into the generator for heating process. By heating, we can separate the refrigerant. So this is preheating because the mixture which is coming from the generator, it has a high temperature. The temperature is equal to the temperature of the generator, right? So that heat basically is given to that. I mean, this is called preheating. So as a result, this will be much cooler because our requirement is that the concentrated solution should be cooler when it comes in the absorber. But this solution, I mean the concentrated solution should be very hot. I mean that energy is basically utilized. Similarly, this one is basically pre-cooling. This heat exchanger is for pre-cooling because our requirement is that it should be very cool when it comes into the evaporator, right? So that's why, I mean, when the vapors are leaving from the evaporator, they have absorbed that heat, that has absorbed the heat. So as a result, its temperature is high. So but we want that temperature to be low as possible in the absorber because absorption process is efficient at low temperature. So that's why that heat is given to that, because in condenser we have rejected the heat, so its temperature is much lower. So that's why the cooling process is utilized. So this is basically the preheater, this is basically the pre-cooler. So we can also have the energy balance for the heat exchanger. The process is same. The energy in should be equal to energy out. So energy in is from that, this is energy in. Similarly, this is 4 is energy in and zero point 0.2 is energy in. And what is out? 0.3 is out and zero point 0.5 is out. So in should be equal to out. So we have the 0.2 energy plus 0.4 energy, that should be equal to energy out, which is energy at 0.3 as well as energy at 0.5. So from this equation, you can have, I mean, or any of the unknown. Basically, in mathematics, the number of equations should be equal to number of unknown. So basically, in order to have a comprehensive analysis, if more equations are, it is more easy to calculate the unknown values. So similarly, we can have the energy balance for the generator. Now this is very critical because actually we have to calculate the value of Qg. I mean, how much input is required from the solar collector. So that input Qg can be calculated through the mass and energy balance. Here we also have to have need to have the mass as well as energy balance because mass is not constant. Let's say first of all, let's talk about the energy balance. So what is coming in? That zero point 0.3 is coming in, and similarly the Qg is coming in, and what is coming out? Zero point 0.4 is coming out and 0.7 is coming out. So through the energy balance, as you can see, the M3 energy at M3 plus the Qg, that should be equal to the energy going, and energy going is the 0.7 energy and 0.4 energy. And similarly, we can have the mass balance. So now you forget about the heat now. Only you have to consider for mass balance just the stream. So there are how many streams? Just the 3 stream. One of the stream is 3, which is coming in, and the 2 streams they are leaving. So 7 stream is leaving and 4 stream is leaving. So mass of the 3 is basically the mass of the concentrated solution. So this is coming in. So that should be equal to the mass of the lean solution as well as mass of the refrigerant, because this is the mass, 7 is the mass of the refrigerant. So mass balance means the mass of the concentrated solution is equal to the mass of the refrigerant plus mass of the weak solution, right? Similarly, we can apply the, I mean, here again, the mass is same. Whatever mass is coming, the same mass is going out. So no need to have the mass balance because M7 is equal to M8. But we need to have the energy balance in order to calculate how much heat we need to reject from the condenser. Let's say that's QC, right? So we need to calculate how much heat we need to reject from the condenser, and that can be again can be calculated by using the energy balance. For example, the energy coming in is 0.7, and what is leaving? QC is leaving and the Q8 is leaving. So the energy balance says that this energy, the energy at 0.7 should be equal to QC plus the energy at 0.8. So here we can have we can calculate from here how much heat we need to reject, right? So this will go on the other side. So what we need is we need the value of the enthalpy and the mass flow rate. And similarly, we can have for the second heat exchanger, and similarly for expansion valve, we know that this is an isenthalpic process. I mean, whatever is the enthalpy at 9, that should be equal to the enthalpy at point 10. In throttling valve, we also call isenthalpic process. So here, the enthalpy, I mean, H5 is equal to H6, or H9 is equal to H10, because we have the two expansion valves. So let's say H5 is equal to H6. Similarly, H9 is equal to H10, right? And again, for the evaporator, this is very critical. I mean, QE is basically equal to the cooling capacity, right? This is basically the amount of the heat absorbed by the evaporator. This is also called the cooling capacity, right? It is normally represented in two units. One we represent in tons of refrigeration. It is also represented in kilowatt, right? If you have the kilowatts, you can convert into tons of refrigeration. 1 ton of refrigeration is equal to approximately 3.5 kilowatt, right? So you can convert each of them mainly. So this is the cooling capacity, or the amount of heat removed from the cooling space. So this can be calculated again by utilizing the energy balance. As you can see, which energy is coming in, the Q is coming in, and similarly the energy from point 10 is coming in, and what is leaving, the energy at point 11 is leaving. So through the energy balance, I mean, energy at point 10 plus energy of the absorb, I mean cooling capacity, that is equal to the energy at point 11. So from here we can calculate the cooling capacity, right? And finally, we can have the energy balance for the overall system. I mean, let's say we don't go into what is inside that system. Let's say if we look at the overall system, in overall system, as you can see, what is overall system energy balance? One is the pump input, right? QG input, heat rejection in the condenser, and similarly heat absorption in the evaporator, and similarly heat rejection in the absorber. So similarly, we can apply the energy balance to the overall system. So in overall system, as you can see, what is the energy in? WP is energy in. Similarly, the QG is energy which is coming into the system. Similarly, the evaporator energy is coming into the system, and what is leaving? The energy leaving is in the absorber, right, as well as in the condenser, right? So this is an overall energy balance, right? And lastly, we can have the performance evaluation in the form of coefficient of performance. So what is, that's the ratio of the cooling produced, which is the output, divided by the input. And input is in the form of that QGin, the heat provided in the generator. Normally the input is also the pump, but normally we neglect that WP, because WP is so small that in most of the time we neglect that. But for more accurate calculation of the COP, you have to include that input as well, whether that is so small, but for accuracy, you can include the value of the work input of the pump. Okay, so as you can see in the previous slide, I mean, you can calculate, you can evaluate the performance or the requirement QG when you have the mass flow rate in each point. I mean, you should know what is the mass flow rate of the absorbent, I mean, in that case, and what is the amount of the mass flow rate uh, of the refrigerant. Then you also need to know the enthalpy at each point, as you can see. So mainly you should know the mass flow rate and the enthalpy in each point, and then you can calculate all of the unknown, I mean these values, and the performance as well. So right, and how can you calculate the enthalpy? I mean, you know that these enthalpies you can calculate from the property chart and property table, but before that you must know that what are the pressure and temperature or the concentration in various points, right? So to calculate the properties, we have various property charts. For example, you can see this chart. This chart is I have copied from the ASHRAE handbook. Right, this is between, I mean, if you have various concentration of the ammonia in the refrigerant, when you use the ammonia water system, ammonia is a refrigerant, water is an absorbent. So when we say zero, that means the concentration of the ammonia is zero at this point. That means you have just the water only, right? And as you move on, let's say 0.1 mean by weight, you have 10% ammonia, the remaining is the saturated liquid. Similarly, so if you move in this direction, the concentration of ammonia is increasing, right? So you need two properties at the time to read the remaining properties. So let's say if you know the concentration of ammonia or the temperature, this is the operating temperature, or you can have the other properties as well. For example, these lines, I mean these lines, they are representation of the saturation pressure. Similarly, these lines are the enthalpy of the saturated vapor. These are the enthalpy of the saturated liquid, right? So this is the vapor composition, right? This is the vapor. So you have different properties from this chart, right? So you can read the required property if you know any of the two independent property, whether pressure temperature or the temperature concentration. So then you can read the remaining property at various points of the system. And again, once you also need to have the enthalpy of the ammonia water vapor. As you can see, if you know the concentration of the ammonia, I mean what is the mass fraction in various point, and these are the temperature, and horizontal lines, they are the pressure. So let's say if you know the concentration and the temperature, you can read the enthalpy, right? So let's say 40% is ammonia and the temperature is, let's say, 60. So that means this line cuts here. So then you can read the properties, right? And similarly, at any point you can read the properties of the ammonia water liquid. We have the other combination as well, which is also called the lithium bromide and water solution. For that system, you also have the property chart. For example, from here, as you can see, you can read the property like this is the solution temperature, and you need one more property. The other property could be this is the saturated pressure. So let's say this is a temperature line. Let's say this is a temperature line. Let's say 80 degrees the temperature. Then what you need one more property. So let's say you have the saturated pressure. So let's say this is the saturated pressure. This is the saturated pressure line. So let's say it cuts here. So this will give you another property. So this property is the mass fraction of the refrigerant. So let's say if cuts here, so you can read that property. So let's say this is 60%. So this is between 50 and 60. So that means maybe this is 59%, right? So the concentration is 59%. So the value of the X is a 0.59, right? The value of the X is 0.59. So that means you should have any of the two property. It can be reversed as well. If you know the concentration and the temperature, then you can have the saturated pressure, right? So once you have this property, you can also read the enthalpy. So in the next graph, you can read the enthalpy of the solution. As you can see, this is the enthalpy in kilojoule per kg of the solution. So let's say it depends on the concentration of the ammonia. So you should have the value of the X and the operating temperature. So let's say the X value is 30 and the operating temperature is, let's say, 50. So you can have the property 125 kilojoule per kg of the solution. So this is how, if you know the pressure and temperature, you can read the mass fraction and as well as the enthalpy of the solution. Okay, so let's try to implement that. I mean, let's evaluate the performance of the vapor absorption system, which is connected with a flat plate solar collector. So let's say this is example one. Analyze the following water lithium bromide absorption refrigeration system operated with flat plate solar collector. So this is basically that heat Q in is through the flat plate solar collector. Right, the machine is provided 350 kilowatt of the refrigeration. So the cooling capacity is that this system, I mean the absorption chiller, that machine is providing this much of the cooling capacity with an evaporated temperature of 5 degrees C. So the cooling in the evaporator is produced at 5 degrees C, right? And absorber outlet temperature of 32. So what is the outlet temperature of the absorber? This is given to be 32, and a condenser temperature of 43 degrees C. So the condenser temperature is 43 degrees C, right? So this is 43 degrees C, right? And this is the 5 degrees C, right? Then the approach at the low temperature end of the liquid heat exchanger is to be 6 degrees C. So the approach temperature is given, right, at low temperature end. So this is a low temperature end and this is a high temperature end. So that means this is a liquid heat exchanger as we mentioned in the diagram. So it says that for the liquid heat exchanger, the low temperature end of approach. So you know that the temperature approach in the heat exchanger is the difference of this one, right? So that means this is basically this is basically the T2 minus T5, right? And the generator is heated by a flat plate solar collector capable of providing a temperature level of 90 degrees C. So in that generator, the temperature is, in order to separate the liquid refrigerant, the temperature is 90 degrees C, right? So based on that, what is the performance of this system? What is absorbent and refrigerant flow rates, and what is heat input? Basically, I mean, this is very important. What is the heat input from the solar connector? Because if you will know this QG, that means you need to know the QA, QU, useful energy. Once you have the useful energy requirement, then you can calculate the specific area of the solar collector, right? So then accordingly you can purchase or you can install based on the specific area of the solar collector. So I mean the given data is, I mean, based on these points. As you can see, there are, I mean, they are numbered. For example, this is T1, right? This is T1, right? T2, T3, 4, 5, right? 6, 7, 8, 9, and then 10, right? So 10 different points are used. I mean, they are represented here. You can use your own points if it is not mentioned on the diagram, but it is mentioned on the diagram, so we can follow the same numbering. So generator temperature mean this is the 90 degrees C. So that means in the generator, so whatever is leaving from that, they have the same temperature. They are leaving from the generator. So that means T1 is also 90. Similarly, this liquid which is leaving the generator, they are also 90 degrees C. So basically the T1 and T7, they are of same temperature. T1 is equal to T7, which is equal to 90 degrees C. Similarly, the evaporator temperature is mentioned. So evaporator temperature mean this temperature, right? In evaporator, temperature remains constant. I mean, the liquid refrigerant comes in, it vaporizes. I mean, the phases changes only. Pressure and temperature inside the evaporator, it remains constant. So whatever is T9, it is equal to T10. Only the phase is changes. So that means T9 is equal to T10, right? And similarly, in the condenser, the temperature is 43. So any of the, I mean, the refrigerant, it has the temperature of 43 degrees C, right, which is equal to T8. And then we are given, let's say we neglect the pump input. So that's why we can have the same temperature. T4 is equal to T5. I mean, whatever is the absorber temperature which is leaving, right? It is mentioned that the outlet temperature of the condenser, outlet temperature of the condenser is 30 degrees C. So an absorber, absorber outlet temperature is 32 degrees C. So let's say that's given. We are also given the liquid heat exchanger, a low temperature approach. This is the temperature approach. So we know that the T2 minus T5 is given to be 6 degrees C, and we know the T5 is 32 degrees C, right? So we can have the T2 as well. So T2 will be equal to 38 degrees C. So let's assume that this expansion is so small that the T2 is equal to T3. So based on this data, what we need to know next? What we need to know next? What do you think? What we need to calculate next?
Sir, we have to calculate enthalpies from temperatures.
Can we calculate by just knowing the temperature only?
Sir, mass flow rate, sir.
Mass flow rate is also not given. We have to calculate that. I mean, we have to calculate the mass flow. Just we are given the temperature only. So from that we have to analyze the whole system. If we just know the temperature only, I mean we know the temperature only and the cooling capacity. I mean this is the cooling capacity of that. Let's say this is the design parameter. Let's say if you want to produce this much cooling and you want to keep these temperature, you have to calculate how much liquid refrigerant is required, absorbent is required, and what should be the size of the solar collector. In other words, what is the value of the Qg? So Qg will be equal to Qu. So these terms you have to calculate by just knowing the temperature of the system only. क्या ख्याल है नेक्स्ट क्या कैलकुलेट करना है? I mean if we know the temperature, can we know the pressure? I mean we know that at 7, for example, at 7, 8, 9, and 10, we have pure water only. I mean, this is a lithium bromide and water system. This is a refrigerant. As explained, this is a refrigerant system. From here to here, up till here is refrigerant. From here to here, this is refrigerant. And we know that, I mean, the generator and condenser, they are operating at high temperature, and similarly, the absorber and evaporator, they are operating at low pressure. Right, so in this range we'll have one pressure, and in this range we have the another pressure. So we know that this is a pure water, right? So we can, I mean this is saturated. I mean let's say if you recall the TS diagram, we have the saturated properties here. So if you know the temperature inside the condenser, which is given to be I think maybe 43 degrees C, so that means we can know the value of the pressure, because if we know, I mean saturated pressure of the water at 43 degrees C, we can use the simple steam table to read the properties, because this is a pure refrigerant, right? Because in property table, if this refrigerant is ammonia or water, we have the properties of the uh, pure working fluid. Let's say in that case is water. We know the temperature inside, which is 43, so we can know the pressure. So that means the saturated pressure is 8.65 kilopascal. So that means if we know the pressure of one point, that means all of the other system is at the same pressure, because we have the two pressure ranges. If you recall the working cycle, we have the high pressure working cycle and the low pressure working. This is the low pressure working cycle. This is the high pressure working cycle. So at this temperature, we can know the saturated pressure. So same pressure will be here. P7, P8, P9, and there the pressure will be different, but we have the liquid refrigerant. In evaporator, pressure will be much lower. We know again the saturated temperature of the evaporator, and we can read the pressure of saturated pressure. We know that here the temperature is 5 degrees C. So at 5 degrees C, we can read the saturated pressure, which is much lower. I mean under vacuum, 0.872 kilopascal, right? Which is, I mean, P9 is equal to P10, because in evaporator pressure and temperature remains constant, only phase changes. So similarly in condenser, this is operated at the same pressure. So P7 is equal to P8, right? And similarly, the other pressure, because we have all of the pressure in this range will be the same. Similar, the pressure in this range will be the same. So that means, let's say, if you know P1, P2, P5, P1 means this one. I mean generator, related to the generator. P6 is this one. P7 is this one, right? So this range, in that range, even this one is the same. right? They are operating at the same pressure. Similarly, the lower portion, absorber and the refrigerant, they have the same pressure. I mean this one, this range P10, right? P3, right? And P4. Where is P3? This is absorber. I mean absorber and evaporator, they are operating at same range. I mean P4, P3, P10 and P9. They are operating at one range. Similarly, this one is operating another pressure range. So once we have the pressure and temperature, then we can read the properties. I mean the enthalpies. Let's say we can use, just to recall you, if you know the properties, pressure and temperature. Let me show you the graph, or this one is, I think. If you know the pressure, let's say this, if you know the pressure and temperature at each point, then you can read the value of the concentration, the value of the x. So once you read the value of the x, then from the next graph, I mean if you know the value of the x and the temperature, then you can read the enthalpy. So mainly you will use these two graphs to read the remaining properties, right? Okay, so let's say, and we also know the H9 is equal to H10, right? I mean this is an isenthalpic process. H8 is equal to, I mean 8 is equal to H9, right? And what is H9 means saturated enthalpy, right? At this pressure, which is also called Hg, right? And similarly, we can have the H10, I mean enthalpy of the at this 5 degrees C. Again, this is also a phase change process. This is also a phase change process. Similarly, at point 7, here, this one, right? This is normally the superheated state. The vapors are in superheated vapor, and we know, since we know the pressure and the temperature, so we can read the enthalpy from that graph that I just showed you. And similarly, for point, let's say for absorber, we know the temperature and pressure. So first we can read X, and then we can read enthalpy. So if we know these two parameters, we can read the concentration, since this is a concentrated solution. So that's why this is represented with the S, right? If we know temperature and pressure, we can read the value of X. And then if we know the value of X and temperature, we can read the value of the enthalpy. This is just reading the value from the chart, right? And similarly, the enthalpy of H4 is equal to H5, because this is an isenthalpy. I mean, if we ignore the input of the pump, then we can assume the same enthalpy as the H4 is approximately equal to H5 if we ignore the input of the pump, right? Similarly, for the point 1, I mean this one we know the temperature and pressure, we can have the enthalpy and the concentration. Now this concentration is the concentration of the weak solution which is coming into the absorber. Let's say we represent with AB, right? This is the solution, concentrated solution. This is represented with XS. So let's say this is which is coming into the absorber. This is, let's say, XS, that which is coming back to the absorber. Let's say this is XAB, right? So then we can read the concentration as well as the enthalpy if we know the temperature and pressure. And similarly for the point 3, this one we know the temperature and the concentration, and then we can have the enthalpy as well, right? Because this X3 is the same as X absorber. It is the same as because same concentration is coming. So that's why if we know the X3 and temperature, we can have the enthalpy. And similarly here H2 is equal to H3 because this is an isenthalpic process. So any of the properties remaining. So do we have calculated all of this? Have we calculated all of this? No, I think still we have one remaining property. Which property is remaining?
Mass flow rate and mass
I
fraction.
think for point 6, the H6 is not known, because in order to have the QG, you should have H6, H7 and H1, but we still don't have H6 because we don't have the mass flow rate, right? We only have is the mass fraction. So that's why we for absorber we have to apply the energy and mass balance. So let's say apply the total material balance on the, mass balance. Material balance is the same as the mass balance. So if we apply the mass balance, just we apply, I explained previously what is mass entering and what is mass leaving. So entering mass is, let's say, M6, and leaving is M7 and M1, right? So if we apply the mass balance, that means M6 is equal to M1 plus M7. But we have the, in terms of mass fraction, we know that this is the XS, as I have given the name is XS, and the which is coming back, it is X absorber. Right? So in terms of the mass fraction, we can write like this is M6 mean this is the strong solution, that means M6 into X. This is the lithium bromide balance, just the lithium bromide balance. So one of the lithium bromide is coming and the lithium bromide is coming out. So what is coming in lithium bromide mean from the total mass, what is the fraction of that? So X6 into M6. Similarly, for this one, this is XAB into M1. So this is the lithium bromide mass balance. We can put this value here, right? And we can simplify, right? So if we substitute this value and M6, so we can have the simplification. We can have the ratio of the M1 and M7, whereas M1 is the mass, M1 and M7, whereas M1 means the mass of the which is coming into the absorber, and M7 is the mass of the refrigerant. So this is basically the ratio of the mass of the absorber, the solution to the mass of the refrigerant, right? So now we can calculate the energy balance. If you apply the energy balance to the generator, we already know, we have the value of the excess, which is in previous slides. We also have the value of the XAB and XC. So we can put that value. So this is 7.07, this ratio. M1 divided by M7 is 7.07. Now we can apply the energy balance for the generator. So if you apply the energy balance for the generator, right, you know that what is energy coming in, what is coming out. So if we put that value, now we can get the value of the H6. So by simplification, H6 is equal to H5 plus this ratio. And previous slide we have calculated H5 and this ratio of the absorber to the mass of the concentrated solution, right? That's, we can put that value. That value is 7.07 to 8.07. We multiply that. If we multiply these two, we can get this value. And if we simplify, so this is the value of the H6 now. So once we have H6, now we need the mass flow rate of the refrigerant and mass flow rate of the absorbent. We are given the cooling capacity. We know the cooling capacity and we know the formula for the cooling capacity through the mass balance, energy balance. So this is the cooling capacity QE through the energy balance. I hope you can do that. For example, what will be the energy balance? What is coming in? H9 H9 is coming in and mass flow rate of the refrigerant, because this is the mass flow rate of the, this is refrigerant and leaving is also refrigerant. So MR H9 plus QE should be equal to energy leaving. So energy leaving is H10, mass of the refrigerant into H10. So from here we can calculate the QE. So QE is basically MR H10 minus H9, and we have calculated the H9 and H10, and this is given. The value given is, I think, 340 kilowatt. That's the cooling capacity of that. Then we can calculate the mass of the mass flow rate of the refrigerant. So we are given 352 is the cooling capacity kilowatt, and we have the H10 and H9. So from here we can calculate the mass flow rate of the refrigerant. So mass flow rate of the refrigerant, which is the mass flow rate of the water vapors, that's about 0.15 kg per second. So once we have the mass flow rate of the refrigerant, from here we can calculate, we know the ratio, right? We can calculate the mass flow rate of the concentrated solution, and then we can also calculate the mass flow rate of the, from the absorbent. So from here we can calculate what is the mass flow rate of the absorbent, and similarly we can have the mass flow rate of the concentrated solution. Right, and lastly, now it is very easy to calculate how much input is required for the generator, because we have the mass flow rate of the refrigerant, mass flow rate of the absorbent, as well as the enthalpies, as well as H6 and M6. So if we put all of the values, then how much energy is required? That's 432 kilowatts. So that means in order to produce a cooling effect of 352 kilowatt, how much heat input is required? 432 kilowatts. So this heat input is provided by the solar collector. So now we know that how much QU is required. So then we can have the based on QU we can have this area requirement for the collector, and then accordingly we can purchase, or we can install, or we can design the solar collector. What about the performance of this system? Performance is the output, the cooling effect divided by the input, and we know the cooling effect is 352 and the input is 432. So lastly we'll have 0.81, the coefficient of the performance, which is connected with the solar system. So is it clear to everyone?
Yes, sir.
Okay.
Yes, sir.
Since we have the short of time, we have condensed the semester up to 7 semesters, so we'll continue, right? I think you don't have any other class. Do you have?
Sir, can you go back, sir, 2 slides back, sir?
This one?
Sir, this one, sir. The next one, sir. T9 and sir, as the temperature of T9 and T10 is same, and sir the pressure is also same. So sir, why their enthalpy is different, sir?
Basically, enthalpy is a combination of the internal energy and the product of the pressure and volume. If you know, the enthalpy is actually the internal energy and PV, right? So there is a role of the internal energy and the specific volume as well. Okay.
But sir, in this case, we are calculating enthalpies from the chart, sir, and if we are using the same temperature and same pressure, so sir, how we concluded that these two enthalpies are different, sir?
It is the same. You can ask the same question, that how come you are adding the heat into the refrigerant without changing the temperature? So I would answer that heat is called latent heat. There is a heat which can be taken from a space, from a system, without changing the system. And practically, you can say, how is it possible you are heating a system and its temperature is not changing? So that heat is basically, that enthalpy is the enthalpy of the phase change, which is used to break the bond of that liquid refrigerant, right?
Yes, sir. Okay. Thank you.
So let me continue. The third application is basically the desiccant humidifier. So this is again, the solar utilization is one of the important application in solar desiccant dehumidifier. I mean, uh, Desiccant dehumidifier, they are used at a domestic level as well as at industrial application. At the domestic, there are certain area of the world we call the humid areas, especially in the African country. The humidity outside is too high. The normal humidity is in the range of 70 to 90%. So that means that's a very high humidity, and the temperature is also very high. So those area called hot and humid areas. So in those areas, in order to produce the cool and the less humidified air, you have the option for the dehumidification process. Cooling as well as a dehumidification process. Right. One of the option is that you can use the normal electric air conditioner. And you know what happens in the air conditioner, that let's say this is an evaporated coil. In that evaporating coil, let's say you have the refrigerant in that coil, which is called the cooling coil. So the liquid refrigerant at very low temperature, so let's say minus 10 degrees C, it enters. So when it leaves, it is in the vapor form, so it absorbs the heat. Let's say this is the air which is coming, and this air is very hot and humid. So when a very hot and humid air come in contact with the surface of this cooling coil, so that means there is a temperature we call the dew point temperature. And we have the two types of the temperature. We call the dew point temperature, it's called a DPT, and we have another temperature we called ADP, apparatus dew point temperature, right? Let's say ADP, apparatus dew point temperature. So when the um, surface temperature of the cooling coil, right? When the surface temperature of the cooling coil, which is called the apparatus dew point, when the apparatus dew point is much lower than the dew point of temperature of the incoming air, then what will happen? The moisture that are present in the air, that will be condensed, right? That will be condensed on the surface of the coil. So as a result, when it will move out, right, that air will be much cooler and dehumidifier. So those condensate that are produced in the evaporating coil, you might have observed in the air conditioner that the water vapors are too high. So there is a pipe in the evaporating coil. So those vapors, they are, I mean, thrown outside from the room, right? So this is one of the way. But for at industrial level application, when you are utilizing the solar energy, right? In those systems, I mean, the other way to remove the moisture is the desiccant, right? And it, I mean, this one, there is a limit for removing the moisture content, right? You cannot have the much dried air, right? Especially for the case of industrial application. For that application, when you need a very dried air, I mean, let's say one of the application is for the product drying. Let's say all of the dry fruits, they are dried, or the powder form, they are dried by using the dried air, right? I mean, that's an industrial application. For that case, you need a special dehumidifier. Similarly, you know that the coffee products, they are produced through a air air drying process. And we also have many other application as well. I mean, if you want to store things for a longer time, for example, especially the bearings or the turbo fans, so the environment in which you are placing these items, that should be free from the moisture. I mean, that environment should be very dried one. Otherwise, if the moisture contents are present, they will damage this, and these products are so expensive. I mean, they are mean to store for a very long time period, especially in the inventory. I mean, these special items, they are stored in the inventory for, let's say, shutdown or for any of the emergency. So in order to have the storage for a long period, the environment should be very dry. Similarly, we have the packaging as well. So because of these commercial application, we should have a very dried air, and this dried air can be produced. I mean, this is, I mean, one of the application just in product drying. You can see, I mean, that has application in the food industry, pharmaceutical industry, right? Even, I mean, you can see a lot of industry where you need a dried air, right? I mean, the special application for producing the desiccant. That's why there is a lot of research going on the desiccant dehumidifier, especially based on the solar energy, right? So what is the physics behind how the desiccant they are working? They are working based on the process of adsorption, right? You know, there is a difference between the adsorption and absorption. What happens in the absorption? Let's say these are the water vapors, they are completely absorbed. Let's say this is a liquid absorbent, so you will have one phase only, I mean the liquid phase only. I mean, these water vapors, they are absorbed in different absorbent, right? So you will just see one phase, I mean the liquid phase. That process is called the absorbent, right? The other one we call the adsorption. This is a surface phenomena, right? This is a surface phenomena, and the water vapors, they are not absorbed, they are adsorbed. I mean this element we also call the adsorbent. It has so huge surface area. I mean there are certain materials that they have so high surface area. I mean let's say I'm giving you the example of, let's say, the silica gel. I mean silica gel is normally placed in the various tablets as well. It can adsorb the moisture. I mean if you take 1 gram of the silica gel, just 1 gram of the silica gel, so it can have the absorption capacity of 800 gram. It has the surface area of 800 gram per meter square. So that's mean it has a very huge adsorption capacity. There are many other as well, like the activated carbon. You can see from here we have, along with the silica gel, we have the molecular sieve, activated alumina gel, right? So they have huge surface area, and because of the huge surface area, water vapors can adsorb on the surface of the adsorbent. And you can see for different range of the relative humidity, different types of the adsorbent are used. For example, let's say molecular sieve, they give the maximum value, I mean the optimum value up to this, maybe up to this one, maybe when the relative humidity is 30%, right? When you need to have, I mean for 30% relative, whereas when the relative humidity is very high, I mean silica gel even can have the relative humidity up to 90%. I mean it has the more capacity to adsorb the water vapors. So what happens, I mean in desiccant dehumidifier, you can see this is the surface area of, it is like a wheel, right? This is a rotating wheel, right? We call the desiccant wheel. So let's say if this is rotating, it this rotating wheel have two surface, its area is divided. Let me show you its front view. Let's say this is a front view, right? I mean the 270 degree of that wheel is used to absorb vapors. I mean from this yellow portion is basically used to adsorb the moisture. Right? The remaining is the moisture that are adsorbed. They are used to remove those vapors. I mean to regenerate. We call it regenerate the desiccant wheel. So what happens? Let's say this is the outside air. Outside air is, I mean, much humidifier. It contains large quantity of the water vapor. So when it moves, let's say when it moves here, right? When it comes in contact with that rotating wheel, I mean these surface area, that's called the adsorbent material. So the water vapors present in the air, they are adsorbed on the surface of this wheel, right? So in this portion, I mean those water vapors are adsorbed. So when the wheel come in front of this area, right, those water vapors, those are absorbed, they are removed. And how we remove? By using a very hot air, right? I mean those air, I mean we use a very hot air, right? Those hot air when in come in contact with the heating coil, so because of the heat, those vapors have high energy, so they are adsorbed. So the desiccant wheel is regenerated. The point here is for that a desiccant wheel, where is the source of energy required? So one source of the energy is for rotating the wheel. So that can also be rotated using the photovoltaic, and similarly for heating that. For heating process, you need an energy. So that heating energy can be supplied through just like the maybe from the air solar collector or through the heat exchanger of the hot water. I mean using the flat plate solar collector. So this is how the desiccant wheel is working. Right. I mean the cycle on which the desiccant wheel are working, they called Pennington cycle. In Pennington cycle is the similar one as I showed you in the previous diagram. I mean this is the rotary desiccant bed in which the outside air is much humid, right? That contains large quantity of the water vapor. So in one part, I mean up to 270 degrees C when the rotor is rotating, so the moisture contents they are adsorbed on the bed. So then at 2 point we have the much dehumidified air. So those dehumidified air is maybe again heated or the is cooled down to supply to the residential building. If it is not a residential application, that means this dry air can directly be utilized for drying the food or for various industrial application. To regain that desiccant wheel, you need a much hotter air. So that much hotter air from, let's say, from that supplied space, let's say from room, it's called the return air from the residence. So return air from the residence is again coming back. So using that solar heater, right, that heat can be used to regenerate that desiccant wheel. So that process can be plotted on the the psychometric chart. I mean, let's say from 1, 2, 3, 4 is from the going one, and this is from the return air. From 5 to 9 is from the return air. As you can see, from 1 to 2 is the heating. This is the heating and dehumidification process. I mean, I hope you know that this is the value of the W. I mean, the amount of the water vapors present in the moist air. So as you can see, compared to 1 and 2, the large amount of the water vapors they are removed from 1 to 2 in the desiccant bed. So mainly how much energy is supplied from 7 to 8, this is the concern, that how much energy is required to have this state to 8 state, right? So that is mainly the requirement. So what you need, you can use the psychometric chart to calculate the enthalpy. So again, that enthalpy, if you know the, I mean, various, I mean, you need two independent property, right? You can locate the point on the psychometric chart if you know two independent property, extensive property. One could be the dry bulb, another could be the wet bulb temperature. I mean, there is a psychometric chart on which 7 properties are mentioned. I hope you have studied in your bachelor degree. I'm not going into that details. So if you know any of the property, normally the directly measurable property is the dry bulb temperature and the wet bulb temperature. So if you know these two temperature, you can have the enthalpy, and from the, and this heat is supplied in the form of sensible heat. So sensible heat is mainly the difference of H8 minus H7. So then you can have that how much energy is required, right? Uh, let's say to to regenerate the rotary desiccant bed. So this energy is supplied from the solar air heater or the flat plate water-based solar collector. Right. So that's the end of this chapter as well. So we have after the mid exam we have covered 3 more chapter. In the next class, we'll try to discuss the solar power. There are power producing power plant as well now. This trend is growing now day by day, that how can you produce the electricity by using the solar energy. So we'll discuss in the next week. If you have any question, you can ask me.
Sir, kindly share the slides, sir.
Right. Okay. I'll share that. Okay.